Join me, Harriet Gould, for the Lab Matters podcast to hear fascinating stories every week from the inspiring people behind the science. In this episode of Lab Matters, Professor Richard Jones reflects on financial crises, regional inequality, and explains his arguments for doing things differently. So today we have with us Professor Richard Jones. Richard is Vice President for Regional Innovation and Civic Engagement at the University of Manchester. Now, hello, Richard.
Hello.
Hi. You're an experimental physicist, an independent science advisor, and you write a lot. You've written about the role of science and innovation policy in addressing disparity between regions, which is incredibly interesting. And we will come back onto that. And you've done so much other stuff as well. And hopefully we'll have the chance to touch on most of it. But firstly, let's get to know you a bit as a person, as Richard Jones. So how did it all start and where were you?
Well, I've been interested in science for as long as I can remember. I mean, I was kind of interested in it at school. Curiously, I was kind of most interested in chemistry probably as someone young, and of course that was in the old days when school chemistry was considerably more exciting than it is now, and one got the opportunity to play with exciting types of transformations. I went to university. Actually, I went to university wanting to do material science because I read there's a great book which is still really worth reading, 50 years on from when it's written, called The New Science of Strong Materials by J.E. Gordon, which is a fabulous book. So I'd read that and I thought, well, this business of trying to understand how materials work and how you can make them stronger or tougher, that sounds really great. I went to university and then I found out that actually material science as it was taught in university was not quite as exciting as I thought it was. And so I think I was not as good at materials. Material science wasn't as exciting as I thought it was. I turned out to be not as good at chemistry as I'd hoped I'd be, and I wasn't particularly great at practical chemistry at university level. So I ended up doing physics. So
All the physicists will be thrilled to hear you say that.
I mean, it worked out fine because I ended up, I studied I've become a polymer physicist. So I've ended up studying materials just from a kind of physicist point of view. But of course, what it's left me with, I just really love the sort of unity of science. And I kind of, I do come at it with physics training, but I'm not totally hopeless at the chemistry side. And I've got interested in other things too. So I suppose whereas some people's scientific careers have got very narrow and focused, I've always had kind of a short attention span. So I've got interested in other things. And as you say, I've been writing a lot recently, been thinking a lot about science and economics and innovation and productivity and things like that. So I'm actually really quite pleased that my job title in Manchester, came to Manchester 4 years ago. My job title is Professor of Materials, Physics and Innovation Policy. So I try to fit it all in.
It certainly sounds like you do. But you wanted to do chemistry before you went into physics. Were you encouraged at school by a teacher? Was there, apart from the cool experiments, what was there something else that led you down that route, or was it just an assumption?
I think, yeah, I'm not sure. I don't. I was really I was really fascinated by chemistry. I think I didn't. To be honest, I think it was slightly despite school rather than because of it. I kind of encouraged my parents to buy me a chemistry set, and they were sort of tolerant of stains on the ceiling from experiments that went wrong. And in a way, possibly my kind of drift away from chemistry was, yeah, it was probably school chemistry was not as interesting as I hoped it would be. So it's
Yeah. Which school did you go to?
I went to a variety of schools. I went to so my father was in the Air Force, so we travelled around loads. So my very early schools were all over East Anglia, Oxfordshire, Pwllheli in North Wales. Then finally they decided they needed to send me to a boarding school because we were moving around so much. So I went to one, first of all, near Aberystwyth, which was and actually that was a good place for I was quite encouraged. There was a good chemistry teacher there called Mr. Redhead, who I do remember with affection. And then I ended up in a school in Staffordshire, it was okay. It was a very kind of sporty school, so I wasn't really I was not really, it wasn't a terribly academic school. So as I was quite a kind of nerdy academic type. And the one thing that did teach me though was I discovered my love of climbing and the outdoors. So that was being kind of at the south end of the Peak District at that point.
Mhm.
Then I did end up climbing a lot.
Oh
And
my.
of course, that came in later in my life because I went to university in Cambridge. I spent 15 years in Cambridge, all in all. I had a short interlude in the United States, but Cambridge is very, very flat. So it was a great moment to when I moved to Sheffield. I moved to Sheffield in about 1998, and finally I was closer to hills and rocks and such like. So I've been in this part of the world ever since. Made the move from Sheffield to Manchester about 4 years ago.
Mhm. It's understandable. And so let's go back to university for a minute with your physics degree. Do you remember what you did? I mean, presumably you remember what you did as your degree. Uh, tell me about it.
Yeah, so it was that there were. I mean, actually, it was a fantastic experience actually, and I should say, I look back on it and I think actually that was a really good education. So
Oh,
it
wow.
was. I kind of focused more on the solid state ends of things rather than the distant galaxies and tiny particles. So I think even in my undergraduate days, I realized I was going to be a kind of fairly down to earth, grubby physicist.
No, no
Uh, and,
principles
and it
or
was great. And I think the Cambridge Physics Department, the Cavendish Laboratory, I think is. I mean, I do miss it actually. It's the one thing about Cambridge I really do miss because I think it's a fantastic institution because it's really diverse in what it thinks physics should be. So, it's got a very kind of Catholic view. Basically, the general view is physicists can study anything, and if it's a physicist studying it, it becomes physics.
mm,
And so that was why, the things I study in many places would be in a material science department or in a chemistry department. But it's good to have that kind of physics lens on things.
mm,
And it kind of gives you a way of thinking, trying to get to the essentials, trying to strip away unnecessary complexity and try to understand, what's going on
mm.
in as simpler way as possible, but no simpler, as I think someone once said.
Indeed. And why is it important that everything in a way is viewed as physics?
Well, polymers is quite a good case in point, isn't it? Because the things I study, a polymer molecule is a long molecule essentially, and that covers things like plastics. It covers biological macromolecules. So, it covers everything from jelly to starch to plastic bags to the sophisticated, advanced functional polymers that people use for light emitting diodes and photovoltaics. And so it does kind of give you that sense that there's some really common properties that all these things have in common, and you can transfer knowledge from one to the other. And it does get a bit ridiculous. I mean, I remember the first graduate lecture I went to was about polymers. I'd not really studied the chemistry of polymers at all. And the lecture was given by Professor Sir Sam Edwards, who is a giant of theoretical physics. And went into this lecture and he started the lecture by saying, well, what is a polymer? And I expected him to, write a chemical formula on the board of, CC, HH or whatever. And no, he wrote down a path integral. And then another great moment was, you do a whole bunch of mathematics on the board and you get to the end and you say, well, at this point, you can recognize this is just a standard field theory, so I need go no further. But, it points out really deep analogies between different parts of the natural world. And, the idea that you can apply ideas, bits of mathematics that have been developed in one bit of physics to all kinds of different materials, I thought was hugely powerful.
Mm. It certainly sounds it. So you graduated. When did you graduate?
1983, 1984, I think.
Mm-hmm.
Yeah.
How did you feel? And what did you have plans for your next step or?
Yeah, so I think I was keen to do a PhD, and I think there were a bunch of us, maybe four of my comrades, as it were. We all sort of studied together and encouraged each other. I don't think any of us thought we were kind of absolutely the top of the class, but we did okay. I think I did better than I expected in my degree, actually. And then, so I was able to get a PhD place. And it was one, again, this scheme of always trying to be a bit applied. I was very pleased to get a PhD studentship that was, a case award, so in collaboration with industry. And that was with ICI in the olden days when ICI was a thing. So I had this PhD with ICI, and it was a curious subject because the industrial supervisors wanted one thing out of it. My academic supervisor wanted a second thing out of it, and I ended up doing a third thing, which is, where I ended up directing the research. I think I realized quite soon that what my academic supervisors wanted was never going to work. And
Can you say what they wanted?
yeah, I mean, so it was essentially about how molecules move around. So it's about how polymer molecules move, how they diffuse. And ICI had a very kind of practical reason why they wanted to know about that. They wanted to understand how various additives that they added to plastic films, migrated to the surface so that they would act as lubricants, essentially.
Mm-hmm.
So that was what they wanted. My academic supervisor had cooked up this scheme. And there was some quite interesting theories going on. So the reason why this is not a trivial problem is because, the way to think about a vat of polymer molecules, it's like a giant pile of spaghetti. All the molecules, they're long, stringy things. They all entangle with each other. And so at the time, theories were just coming through to see how you could understand how anything could move through this giant mass of stuff. And there was a very interesting problem, which was if you've got a linear polymer, it can kind of, well, the great French theoretical physicist Pierre-Gilles de Gennes came up with this notion of reptation, where he said, oh, the way you should think about a polymer is imagine a snake in long grass, and the snake can always move through the long grass because the rest of its body follows its head, if you see what I mean. So it's like this snake-like motion. So that formed the basis for the kind of classical theories of polymer motion. Then the question comes, well, if what happens if the snake had three arms, as it were, or if you had a star-shaped polymer, then it wouldn't be able to move through. So my academic supervisor was actually quite keen to get me to measure the movement of a star-shaped polymer, but it turned out that the technical difficulties of tracking the individual molecule were going to be just too great. So in the end, it ended up doing something else.
Which was?
Well, then I started thinking about what happens if the polymers are not chemically identical. So the polymers were different polymers. And it turns out most polymers don't actually mix. And that's why plastic recycling is so hard. If you just take a random mixture of polypropylene, polyethylene terephthalate, heat them all up, they all separate. And there's some really kind of basic physical reasons why that's the case. So most different polymers don't mix, but occasionally you get pairs of polymers that do mix. And it turns out that the reasons why most polymers don't mix are exactly the same as if they do mix, then they'll mix very strongly. So in a sense, the diffusion is enhanced because there's a chemical similarity between the two polymers. And that's really just because of the multiplicity. That's just because you multiply up the interactions. So, if you've got two single molecules, they probably have an unfavorable interaction, but Brownian motion can overcome that. If you tie 100 of them together, then that multiplies it up so that either mostly they just don't like to mix, even more so. But if they do mix, then the favorable interactions are additively, they all sum up, and then diffusion looks kind of anomalously fast.
And is it easy enough to go with the separation? For example, in a recycling plant, can they stick everything in the same melting pot and then take out the separate melted elements, or do they have to separate it before?
No, you absolutely have to separate it before. It's really, this force that makes them separate is so strong that what you get is just a very a very well, not only is the force that separates them strong, but then the interface between the separate components are very weak because they don't form a very strong interface. That was something else actually later in my career I kind of looked at a little bit. But yeah.
So you did that for your PhD, and with that in place, what happened next?
Well, then I got the chance to go to the United States. So I got an offer to go to Cornell University to do a postdoc in Cornell. And there I worked with a great scientist, a man called Ed Kramer, who I think was such an inspirational scientist to me. My PhD was fine, but I think I really properly learned to be a proper scientist in Cornell with Ed Kramer. And I worked on some kind of quite related problems, but they were, he was so, he was such a great boss, both in terms of, he had this fantastic scientific understanding. He was a really great experimentalist. So I probably learned a lot about experimental techniques there. But also he was really just interested he was very well connected. He used to do lots of consulting for companies. So he was very well connected in understanding, the applications of these things. So that was a great experience for me. It was just a fantastic time.
He sounds like a supportive person to have around,
Yeah,
and creative as well, by the sounds of it.
absolutely.
To have that kind of environment. So you were there for a year and then back.
I was there for a bit more than 2 years. So I did. I mean, there were sort of three distinct things that happened there. I think the science problem I was working on, I kind of stumbled on it by accident. Actually, it's one of these things where I was trying to do one experiment, and this interesting phenomenon turned up. So what we were trying to do, we tried to solve the problem of how do you just pick on one molecule. I've got this soup of spaghetti-like molecules, and I want to understand how one of those molecules moves around. How do I, if you like, color it in or, label it? And, label it in a way that doesn't affect its normal properties. So the kind of way that a number of scientists had thought this should happen would be, so a polymer like polyethylene or polystyrene, it's got a lot of hydrogen in it. It's basically carbon and hydrogen. So the thought was if you replace the hydrogen by deuterium, the deuterium is, it's pretty much the same as hydrogen. The general, the consensus view is that isotopes are chemically identical, but they have, they've got a different relative atomic mass. So the idea was that we labeled some of I was working on polystyrene actually. So we had some polystyrene. We labeled some of it with deuterium, and then we could follow where it went around by a very cool technique that I might say a bit about in a moment. But what we found was that actually they clearly weren't chemically identical because the deuterium, the deuterated version, ended up going to the surface. So it ended up, essentially it behaved like a surfactant. It has this tiny difference in surface energy. But again, this same weirdness of polymers, because everything's additive. it kind of multiplied that effect. So if I took the difference between, say, benzene and deuterobenzene, there is a slight, to get technical about it, deuterium is slightly heavier than hydrogen. So the CH bond, the CD bond is slightly shorter and stiffer than the CH bond. And normally this is just too small an effect. It's actually worth about, 1/10,000th of KT. So, it's totally swamped by Brownian motion if you take small molecules. But the thing is, for a polymer, you can get 10,000 of these things joined up in a string, and the effect is totally additive.
Mm-hmm.
So by the time you get a very long polymer, even that tiny difference is enough to make them, want to separate out. And in this case, by the deuterium wanting to go to the surface. So that was a kind of really striking and unexpected effect. But it was then a very clean system. So we could then test out theories of surface segregation that would apply to other polymer systems, but we could really test it very cleanly against the theory. So that's what I did there. It was all fun stuff.
Yeah, it sounds it. You mentioned that the technique was quite cool. Is it's now a good time to talk about that?
Yeah, it's kind of great that I can talk about this now, because the technique, essentially, it's an application of a bit of physics that was discovered about 200 yards away from where I am. So, and this is, a long time ago. Ernest
Where you are
Rutherford.
being at the University of Manchester.
Yeah, so Ernest Rutherford, sometime in the early part of the 20th century, discovered the nucleus. So it's like this is a kind of totally seminal discovery in understanding the structure of matter. He discovered that atoms had a nucleus in the middle, so most of their mass was concentrated in a very small place. And the way he discovered it was by an experiment which is called Rutherford backscattering. So if you fire an alpha particle at a piece of matter, most of the alpha particles just go straight through, but every now and again one just bounces back, because if it hits the nucleus, then you just get like an elastic collision. It's just a complete billiard ball like collision, and the alpha particle bounces back. So we were able to use an adaptation of that technique. Essentially, basically what you end up doing is the deuterium that you're looking for, you just knock it out of the material, you measure the energy, and the energy tells you essentially how close to the surface it was. So it's a way of measuring the concentration of deuterium close to a surface. And again, I keep talking about clean experiments. It's a very clean experiment. It's very easy to interpret, and it's very definitive in what it tells you.
Mm-hmm. So you spent 2 years doing that, roughly speaking.
Yeah.
You weren't tempted to stay in America?
I sort of was, yes and no. I think the science of it was great. I kind of, and there were various options opened up, but I missed the UK. I don't know. I wasn't
The
able
weather.
to, I wasn't able to become a kind of an American right away. And so I was quite keen to come back. So I applied for jobs and eventually got one.
Lab Matters is brought to you by the award-winning temperature control equipment from Polyscience, available worldwide. Polyscience, changing the world of temperature control forever. So where did you back in the motherland?
Yeah,
Your first job was?
it was at Cambridge. So Cambridge had me back. I got a assistant lectureship at Cambridge. And that was actually also supported by ICI. So the ICI connection came back in. I mean, what happened? I mean, it's an interesting time because, we're now talking, this is now in 1989, we're now talking. And of course, the UK academic system was, it had been really stretched for funding. Funding had been really tough. So, even in Cambridge. So there weren't a lot of jobs around. But again, the same professor who taught me polymer physics, he'd gone to both ICI and Unilever and said, how about it? Will you kind of help us, just bung us some money to support, lecturers that will work on bits of science that are interesting to you? So I came back, and it was, as I say, essentially as an ICI sponsored lecturer in Cambridge,
Mm-hmm.
and working on polymer physics, so obviously things that they were interested in from their business point of view.
Sounds like the perfect setup.
Mm.
So I don't know where to go next. We could go in the order that it's written in your bio, that you've written extensively. Now this really is interesting because it touched on that funding point that you just made. So you write a lot, and you've got a blog, in fact, softmachines.org.
Mm.
So if we want to have a look at what you've written, we can always go there, softmachines.org.
Yeah.
But you write about the role of science and innovation policy in supporting regional disparities in economic regions.
Yeah.
And that's like, I mean, people are trying to figure that out politically, socially, all over the place at the moment. And you've written how science and innovation can help that. Do you want to tell me a little bit about that?
Yeah, so that's a kind of a long and winding story, actually. It's not as everything's not straightforward. I mean, so yes, why have I got a blog called Soft Machines, I hear you ask? It's because I wrote a book called Soft Machines. And why was it called Soft Machines? So the book, so we've now moved forward to the kind of to about 2004, isn't it? That's when so I'd moved from Cambridge to Sheffield. So I finally managed to get myself away from the flatlands closer to the hills. And that was actually, I mean, the reason I moved is, also just a little bit of relationship to my strange relationship with chemistry and you know, Cambridge was a fantastic place. The Cavendish laboratory was marvelous. It wasn't always easy to kind of collaborate across different disciplines in Cambridge. And so I'd been talking to another great scientist, my age, more or less, Tony Ryan, who was at that time at Manchester. And Tony had had quite a similar sort of career path to me, but he was a proper chemist. And so the two of us said, well, why don't we both see if we can go to Sheffield and then we can kind of collaborate, we can kind of set something up. There's not a lot of polymer science happening there at the moment. So if you like, we'd be starting something new and we could start out bringing together kind of chemistry and physics much more closely. And so that's what happened. I was thinking a lot about nanotechnology at the time, because it was the time when nanotechnology was very fashionable. And there were lots of people making big claims for it. And essentially there was a kind of conceptual view of it that nanotechnology would look like, mechanical engineering shrunk down to the microscopic stage. And I was sure that was wrong. And I was sure that was wrong because of, what we were understanding with polymers, what polymer molecules did. And then, and increasingly, I was trying to find out what was happening in biology a little bit. And the way that biological systems work is different too. So I had this idea that, nanotechnology would be, I mean, the way I summed it up would be, it's a soft machine. And that's a kind of allusion to two things. My bit of physics, more broadly than polymers, we could talk about soft condensed matter or soft matter. And that's the idea of soft matter, is it's matter where all the forces are kind of weak compared to Brownian motion. So bonds are constantly being formed and they're constantly being broken apart again. Everything's being shaken around. It's the picture of soft matter is one of everything's malleable, everything's changing. And, that's what biology is. Biology is made of weak bonds, associations that form and unform, things move around, Brownian motion jiggles everything. So I wrote this book called Soft Machines, which was essentially to say, this, I think, is the right way to think about nanotechnology. And, by the way, I think I was right. I would just like to say at the moment.
I'm
And
very
I
happy
think,
to hear it if you wrote a book about it.
so, I've kind of, I'm very happy I wrote that book, because I think I was on the right track. But Soft Machines, of course, there's a well-known prog rock band and a book by William Burroughs called Soft Machines as well. But anyway, that kind of, because it sort of arrived at a time when nanotechnology was quite fashionable. You may remember Prince Charles, as he then was, wrote an article saying it was all terribly dangerous and we'd be all turned into grey goo. So
Okay.
because I'd kind of written this book at that particular moment, I got sucked into some of these national debates about how nanotechnology, might or might not affect society. And so that kind of got me interested in thinking about science, society, how that relationship works. Then I worked a little bit for the Research Council, had a couple of years working for EPSRC, to sort of guide their nanotechnology policy. And then I went back to Sheffield. Well, I never left Sheffield, but I'd been on secondment to the Research Council. But then I went back as into the world of the of trying to think about science and innovation across the whole of the university. So I had this role as PVC for research and innovation. And that, I suppose, is when I really started thinking about economics in a very hard way. Because Sheffield is a city that did very badly out of deindustrialization. The loss of its steel industry really had a huge impact on it economically. And so now we're in about 2008, 2009. I think I started in 2009 in this new role. And there'd just been this huge financial crisis. Basically, we all thought we were all bankrupt, as it were, which we sort of were. It just took a long time to take place. But at that time, we kind of realized in a city like Sheffield, the university was pretty much the only major institution that was still standing. And so thinking, okay, we've got to be serious now. What can how should the university be supporting industry and business in its city? Then started to be something I thought about, really practically as well as kind of academically. And so that kind of led me into thinking a lot about regional economic development, the role of science and innovation in regional economic development. Mm-hmm. Yeah, that took me into trying to understand what economists were writing and trying to influence some of those debates.
And do you think you've found the formula for solving regional disparity?
Well, I haven't found the formula. I mean, I think the first stage is that we've actually kind of identified and quantified what those regional disparities are.
Mm-hmm.
And so, I wrote a policy paper with Tom Forth as a data scientist from Leeds. Nesta helped support us to do that, and that was called the missing 4 billion. And it was just a kind of numbers exercise. We just went through the numbers and just established how much there, how much of R&D spending in the UK is concentrated in the greater southeast. And actually, interestingly, what we found was that public funding is more concentrated than the industrial funding. So in a way, this made us think, actually, this can't be right, because if I lapse now into economist speak, economists will say, well, the state needs to support R&D because the private sector can't. The private sector will never invest as much in R&D as would be good for the country because they can't get all the benefits from it. To some extent, science is a public good. You do the experiments, you publish the papers, everybody finds out about it. So in a sense, it's hard to ask a company to do that because they don't get all the benefit from it. So obviously, they will try and support science and they'll try and protect it by trade secrets or by having patents or whatever. But fundamentally, they won't do as much science as the country needs for entirely rational economic reasons. So an economist will say, well, that's why the state needs to fund it. So the state funds R&D so that businesses can take advantage of that. They can then convert it into products and money and growth and all those sorts of things. But then the argument then says, well, where are you going to do this? And it seems to make sense that you would want to have some rough match of where the state spends money on R&D and where companies do. And as I say, the strange thing was that we found that, to be fair to Oxford and Cambridge, which is I will be, Cambridge, for example, it has a gigantic truckload of state money going into it, into R&D there, but then equally huge numbers of companies set up there. So in a sense, that's what you want to see. The state puts in money, companies put in even more money, it creates prosperity. So kind of Oxford and Cambridge, well, Cambridge especially, Oxford a little bit, maybe slightly less so. That's they kind of work like you'd expect. But London was different. It was interesting that London gets huge amounts of public R&D money, but not actually that much company R&D money. Whereas where are companies spending their R&D money? Well, quite a lot of it is in the Northwest and the West Midlands. So, you look at West Midlands where you've got JLR, you look at the Northwest where you've got a whole bunch of chemical companies, a bunch of pharma companies, BAE Systems. So there's this kind of mismatch between where the state spends money and where the private sector spends money. And of course, the risk is that the private sector follows the signals. And so, the big thing that happened in the Northwest is that AstraZeneca, packed their bags from Alderley Park and moved to Cambridge. Why wouldn't they? That's where all the skills and R&D money is being put. So I think that, that makes it very clear that there is this link between concentration of public sector R&D funding and regional economic inequality. So, we were able to kind of make those arguments, I think, in a relatively, in a fairly convincing way. And I think we did land some of those arguments. So I think, the Levelling Up white paper actually did have, for the first time, a kind of explicit section saying, this imbalance is not great and we ought to do something about correcting it. So, yeah, that was.
You are in it. Is that right? You're in it.
I think it's fair. I think I don't have any problem in saying I think that those arguments reflect the arguments we made in our paper. I think absolutely. So we got there. I had this very bizarre period as well. So as you kindly said, I write a blog and I publish lots of stuff on the blog, which is sometimes quite nerdy and but I had a very interesting moment. I think it was, where are we now? We're in, it's just about late November or early December in 2019. So after the election had been called, but before the election had taken place, I was in my office and I got this phone call from this bloke and he said, "Oh, hello, is that Richard Jones?" "Yeah." "Oh, I'm calling you from The Guardian." "Oh, yeah, how interesting." So I just wanted to get your reaction to the fact that your blog has just been quoted with admiration by Dominic Cummings as an example of the sort of thing the new Conservative government would do if re-elected. What's your reaction to that? So I did my best to sound not totally shocked. But anyway, it was true. Dominic Cummings had picked up my blog and read my blog and said, in the blog, this was a piece that did say quite a lot about regional innovation. So one could see that argument was made in, it had landed amongst people who subsequently, or even at the time, did turn out, at least for a short while, to have some influence in government.
Well, hopefully it'll be picked up again.
Well, I hope so. And, the arguments I make, I think, nobody will dispute that the UK has got a serious problem of productivity growth. Productivity's not grown. It's grown very weakly since, way to the financial crisis or even before, probably to the mid-2000s, but certainly since 2008. And actually, I think that's got a huge amount to do with everything that's difficult in the country's economy and its politics, because that's directly translated into flat wages. So the reason that wages haven't grown is because productivity hasn't grown. So, whatever we're doing about trying to connect innovation and science and technology to economic growth, it's not working. And then, on top of that, we've got this regional inequality problem that, particularly, I'm sitting in Manchester at the moment. The UK is really unusual by the standards of most developed countries. In most developed countries, it's the cities that drive the economy. So, if you go to Germany or even to France, centralized though it is, Lyon is a very strong economy. Munich is a fabulously rich city. So the second cities in most countries are drivers of the economy. The UK is different. So Greater Manchester, the West Midlands, Glasgow, these have economies, their productivity is actually lower than the UK average. So there's something very wrong about how our economy is working in terms of how well our cities are working. So that's another dimension, an argument that I've been trying to land. Of course, it's not just me that's saying that, and we've got some very, very excellent economic geographers and economists saying that now as well. So I think the fundamental problems, the diagnosis of what's wrong with the country, as it were, I think it's actually now quite widely shared on most, in most parts of the political spectrum. So it's just a question of getting some sensible ideas about what to do with it, and then implementing those.
Mm-hmm. And you're already a scientific advisor for Greater Manchester and the combined authorities there. Would you go to central government?
Well, I talk as much as I can to anybody who'll listen, both in terms of politicians, but also the civil servants, politicians on both sides. So anybody interested in economic growth, I will do my best to bend their ears with what I think about it. I mean, the relationship with Manchester is an interesting one, because in a sense that follows. So I moved to Manchester about 4 years ago. Well, when Tom Forth and I wrote The Missing 4 Billion, the argument we made was, if we carry on doing things the same way, we'll still get this concentration. And the concentration of research funding, it's kind of easy to see why it happens. It's because, if you've got a lot of money supporting science, that attracts good people. There's great facilities. You do even better science if things are funded. If you're funding according to, excellence, how well people do in writing grant proposals, there's a natural self-reinforcing effect to science funding, and without people even thinking about it or being conscious of it. So Tom and our argument was, if you want to change things, you have to do things differently. And the way, one thing that you could do is just devolve some money to cities and regions. So maybe probably not very much money, but just to start on this job. And then the counter argument to that, which I hear all the time from people in London or from Swindon, is, well, we could give money to Manchester or Sheffield, but they'd just spend it on hanging baskets and roundabouts. So they wouldn't be able to make good decisions about how to spend money on science and technology and innovation in a wise way. And so I thought, okay, that's a fair comment. So in order to counter that, you'd have to say, well, we need to create some kind of capacity, some structure to make those good decisions. So when I came to Manchester, and I should say, this is the university in Manchester is very close to its city, and the kind of links between the university and its management and city leaders are very strong. And, Nancy Rothwell is undoubtedly, part of she's obviously part of the great and good of Manchester, but, there's a coherence to the way that the city operates that the university is part of. So I was involved in early discussions about this, and said, fair enough, that's a good challenge. We should set something up that would meet that. So we set up this organisation called Innovation Greater Manchester, which kind of brings together the universities. And, that's not just the University of Manchester, that's Salford, Manchester Metropolitan, Bolton, the Royal Northern. So all of the city universities cooperating. Then, the private sector, so representatives from the materials and manufacturing sector, from the life sciences sector, from the digital sector. So you get that kind of industry voice, and then you get the combined authority and the kind of political authority that comes with the elected mayor. So if we got all those three things together, working together, we could say to government, look, we can be a partner. You can trust us with some, with some money we can work together to kind of see what we can do to boost the innovation economy of the city. So it was in that, I got fingered to be the scientific advisor for this organization, as it were. But that's really the thinking. It's about bringing together industry, academia, and the city region authorities, so that we can all work together to drive up innovation, drive up private sector R&D, to create productivity growth and prosperity for everybody, really.
Well, it just sounds so fantastic that this sort of work's going on behind the scene. And I'm so glad that Dominic Cummings did pick up on your blog, because it does give us encouragement that more people will. Did he invite you to number 10?
He did, yeah. No, I went to number 10 a few times. Yeah. It was interesting.
Very much in the works. Excellent.
Yeah.
Well,
I mean, and also, I mean, just to be blunt, I mean, obviously, lots of other people wanted to talk to me, in a way that's been more lasting. Dominic Cummings, he didn't stay in government for very long for all those reasons that we know. But in a sense, it gave me, I think a lot of people were quite keen to talk to me while they thought that Dominic Cummings was important. And then I've kind of, people still talk to me. So that's all good.
And so you've effectively cracked open the regional economic atom.
I would say that.
So look, just before we go, a couple of questions which probably seem quite trivial compared to everything just spoken about. But firstly, how are we going to prove you were right about how to think about nanotechnology? What's got to happen? We've just had, what was his name? I should have noted his name down. The boson hit theory. He's just died, and he was proven right at the end of his career just now.
Well, I mean, I should say, I wouldn't want to, it's not just me that was saying this, and it's been a line of research that's been very important. But I would, if you wanted an example of, what's nanotechnology ever done for us, I would say that the mRNA vaccines are a major example. So, mRNA as a, that new technology that came from BioNTech, came from Moderna, the RNA part of it is marvelous, and getting RNA to make the body, if you like, create its own antigens, and so it kind of manufactures the vaccine in situ. But in order for that technology to work, you needed to get the RNA, you needed to wrap it up in a kind of little envelope. You needed to be able to get that envelope to be injected into the body, to find its way to the cell, to get into the cell, and then release its load. And that's it's a very cool piece of science that was done. People like Robert Langer in MIT was key for the Moderna vaccine, developing that delivery mechanism. That, I think, is a pretty telling. Well, I mean, that's absolutely a great example of that soft approach to our technology working. So I think, I'm going to take that as some degree of vindication of what I was talking about.
Good. And then finally, in a perfect world, what are your greatest hopes for the future of science?
Well, I think we do. I am going to sound slightly pessimistic. We've just had, we're now in the second decade of economic stagnation, and it's worse in the UK, but it's actually a general world phenomenon. It's worse in the UK. So we've somehow managed to break the link between scientific advance and economic growth and, the kinds of, the things that people expect science to deliver. Even before the pandemic, we were seeing the increase in life expectancy in the UK had started to slow down. So I think we've somehow got to a state, we've broken the link between fantastic science and, believe me, there's just marvelous science happening all over the place, but somehow we've broken the link between, or the link has been broken between scientific advances and economic prosperity and, people's well-being. So I think we've got to work on, reinstating that link. So it's fairly clear what we've got to do. We do need to get that link to economic prosperity better. We need to get the link to people's health outcomes better. Another thing about the inequality that we see across the UK is that translates into health inequality. There's 10 years difference in life expectancy between Oxford and Oldham, to give you two examples. So we've got to get that right. And then we've got this huge transition, to get to net zero, we've got to totally rebuild our energy economy. And, again, great science there. And, the sorts of, other bits of nanotechnology that are, that could help there are, I've been working with a spin out company from Cambridge on things that would make solar cells quite a lot more efficient. So, all the science that goes into getting to a net zero economy, we need to accelerate that and make that work faster. So I think, I'm really optimistic about science. I think it's really still fantastic stuff's happening. We just slightly lost the link between science and, delivery to productivity, economic outcomes, health outcomes, transition to net zero.
Well, hopefully we can re-establish that link and things will start looking up. Richard, in all honesty, I'd like to talk to you forever, to be honest. I think there's so much more that you could say. But thank you so much for everything you have said and for your time today. It's been an absolute pleasure.
Thank you. Pleasure's mine.